Hi, this is A-level physics. This is orbital mechanics. I've got an energy question. It's a complex one. So if you want to pause it, have a go at this, and then I'll explain how to do it. So we've got a spaceship of mass 16,000 kilograms at an orbital height of 850 kilometers above the surface of the Earth. It moves into a position 450 kilometers above the surface of the Earth. Considering the kinetic and potential energy of the spaceship, calculate the total change in energy. Ignore any air resistance in the upper atmosphere. So to answer something like this, there's a lot of underlying principles that we need to be aware of. So I'm just going to talk through these and then come back to the question to answer it. So what is the potential energy of a mass in orbit? Well, potential energy, historically GPE, for a uniform field is mgh. So for a large radial field, what we can actually do is substitute in the gravitational field strength equation, which is minus gm over r squared. Substitute that in, that gives us potential energy, which I'm going to call U, equal to, so I've got mass times g, we've got an equation for g, so minus g m multiplied by the other m, times the height, which we're going to call r, divided by r squared. So the r's cancel, and we're left with potential energy of a mass in orbit is minus g multiplied by both masses, mass of the planet and the mass of the object, over r. So make sure you've got that down, and then we'll look at the next point. So the next thing is velocity of a mass in orbit. Now you might already know this, but let's just have a look. So if you're in orbit, say this is the Earth, and you're in orbit around the Earth, you would have a velocity that's at a tangent at any point in time to the circle that your trajectory is. Velocity v. So the thing that's keeping us in orbit is the gravitational force, and it's making us exhibit circular motion. So the gravitational force is g m1 m2 over r squared, and that is equal to the centripetal force mv squared over r. So what we can do there is cancel the m's, cancel the r's, and we get an expression for velocity, or v squared, as gm divided by r. So we're also going to need this. Let's move on to the next bit. So kinetic energy, classically, kinetic energy is a half mv squared. And what we're going to do is to substitute in the equation that we just got, v squared is gm over r, and see what we get. So the kinetic energy is equal to a half m times gm over r. So we've got g mm divided by 2 lots of r. So that is the kinetic energy of a mass that's in orbit. And what we can do now is get the total energy by adding the kinetic energy to the potential energy. So the total energy of a mass in orbit, so the total energy, which I'll call T, would be equal to the sum of the potential energy plus the kinetic energy. So the potential energy is minus g mm over r, plus the kinetic energy, which is g mm over 2r. So essentially we've got minus 1 lot of g mm over r plus half a lot of g mm over r. So it's minus 1 plus a half. So an equation for the total energy is minus g multiplied by both masses divided by 2 lots of r. That equation is exceptionally useful for calculating the energy of an object in orbit. It's not on your data sheet, so if you're going to use this, you need to remember it. So now with this equation, we can do this question. So we just need to use that equation for 850 kilometers above the surface of the Earth, and then use the equation again for 450 kilometers above the Earth, and then do the difference between the two total energies. So if you want to have a go at that again, please do, and then I'll show you how to do it. So the total energy is minus G mm over 2r. So this is for 850 kilometers. So minus 6.67 times 10 to the minus 11 multiplied by the mass of the Earth, which is 5.97 times 10 to the power 24, multiplied by the mass of the spaceship, which is 16,000, divided by 2 lots of the total height from the centre of the Earth, which is 7.22 times 10 to the power 6. So that gives a total energy at 850 kilometers of minus 4.412 times 10 to the 11 joules. So then we just need to repeat this for 450 kilometers, so make sure you've got that value. So same again, same formula. Total energy is minus G mm divided by 2r. Then put our numbers in, so it's minus 6.67 times 10 to the minus 11, multiplied by both masses, 5.97 times 10 to the 24, multiplied by 16,000, divided by 2 lots of 6.82 times 10 to the 6 meters. So that gives us a second total energy of minus 4.671 times 10 to the 11 joules. Then finally we just need the difference between our two values. So we're going to do the total energy at 850 kilometers and subtract the total energy from 450 kilometers. So the change in energy is minus 4.412 times 10 to the 11 joules. Subtract minus, so it's going to be an add 4.671 times 10 to the 11 joules, which gives a change in energy for the answer of, to two significant figures, 2.6 times 10 to the power of 10 joules. Hopefully that went okay. Thanks for watching, and I'll see you soon.